concrete walls. There's a place for us where we could go, where we could be alone. Between city lights, we don't have to hide. I wanna go, do you wanna follow? There's something in the air, I can't explain it, but it's there. Ain't nobody gonna find us in our secret love affair. I don't wanna have to hide no more, it shouldn't be unfair. I wanna go, and I wanna know, do you wanna follow? Baby, do you wanna follow? Come with me, do you wanna follow? Baby, can't you see that? I wanna go, and I wanna know, do you wanna follow? Baby, do you wanna follow? Come with me, do you wanna follow? Baby, can't you see that? I wanna go, and I wanna know, do you wanna follow? I can't understand why we can't hold hands, but they don't know what we have is real love. Aren't you sick and tired of having to hide? I know a place, do you wanna follow? There's something in the air, I can't explain it, but it's there. Ain't nobody gonna find us in our secret love affair. I don't wanna have to hide no more, it shouldn't be unfair. I wanna go, and I wanna know, do you wanna follow? Baby, do you wanna follow? Come with me, do you wanna follow? Baby, can't you see that? I wanna go, and I wanna know, do you wanna follow? Do you wanna follow? Baby, do you wanna follow? Come with me, do you wanna follow? Baby, can't you see that? I wanna go, and I wanna know, do you wanna follow?
What's up, everybody? Welcome to the stream. I am Joshua Bardwell. But you already knew that, didn't you? Did you? You already knew that. I am super excited to be with you guys today because I've got some very, very special guests on my stream today. You know, you guys know that normally on my stream we do Q&A. You ask questions and I answer your questions. But today we're going to be asking questions of some people who are probably some of the smartest people out there today about FPV motors. And let me go ahead and introduce them to you guys. Who is this guy talking? Game of Drones. Shut up. Get out of here. You know who I am, aren't you? Here we go. I've got right here, this guy we're looking at right now is Ryan Harrell. Ryan is the founder of miniquadtestbench.com, a website where he tests motors and ESCs in more depth than just about anybody. In addition, Ryan is the designer of frames for Lumineer. I think whenever I have questions about how motors perform, I have always gone to Ryan and asked him. In fact, we've got some interviews we did on my channel previously where we talked about this stuff. And yeah, so that's right. Ryan has a lot of test bench. Not that Ryan doesn't fly, but he's got a lot of test bench experience with motors, probably as much or more than anybody else out there. Now, this guy, let me pin his video. A lot of you guys may not know Chris Rosser. Chris Rosser has just, in the last couple of weeks or maybe months, started doing a whole bunch of analysis on frames and motors from an academic background. Chris's background is in aerospace. I'll let him tell you what his actual degree is in or whatever. But he's been doing CAD analysis of frame, resonance, and motors. And Chris recently released a video making some pretty interesting claims about how motors work and what the best motor is. And I'm really excited to dive into those claims. Now, the last person on the stream, let me remove pin. There we go. This handsome guy is a dentist. No, he is in fact a dentist. This is Kebab FPV Bob Roogi. In addition to making people's teeth beautiful, Bob is a frame and motor designer. He sells his frames and motors over at fpvcycle.com as well as other places. And the reason Bob is here is because I think Bob has flown more different varieties of motor than just about anybody out there. Bob will buy motors from his manufacturer and he'll say, well, I ordered a 1303, a 1303.25, a 1303.5, a 1303.75. He'll order them and he'll try them all. He's flown and he spends a lot of time thinking about how motors fly. So we're going to talk about motors. I'm going to be checking out you guys as well. Here we go. Here in the chat, I'm going to be checking you guys out. If you want to leave a super chat, and I'm sure there's going to be a lot of questions. We're going to be taking questions from the chat, but I have a feeling we're going to also just be talking and arguing with each other so much. So if you want to make sure your question gets answered, definitely hit the $, leave a super chat, and I will also be checking out the Discord. But I want to start, Brandon Bentley. Bob is responsible for improving the dental health of the FPV community. That is actually true. I want to start. Let me remove Bob's pin. Okay. I want to start with a claim that Chris made in his motors video, that the number one, that the way to think about a motor is performance. If you could sort of pick one thing to define a motor's performance, you might pick the torque of the motor, and that's going to determine a whole bunch of other performance characteristics. And Chris said that the torque of a motor is basically related to the volume of the motor stator. That's it. And not a whole bunch of other, like a lot of people think that the shape of a motor decides whether it's torquey down low or torquey up high. And Chris, you said the volume of the motor and not the shape determines the torque. Is that right?
Sure. So I guess I should preface this by saying that my aim with that video was to try and get some points across, some simple rules of thumb that could really help people with making choices about what motor to buy. And I know that motor performance is a hugely complex topic, but I wanted to try and pick something that has a real impact. And I felt that the envelope volume of the stator, based on the analysis that I did, which you can watch in the video, really the envelope volume of the stator was one of the critical parameters. And it's not the only parameter, but it's one of the easiest ones that people can quantify and that people can use to make good choices about what motor to get for a particular build.
I don't think anybody would argue that the volume of the motor is important. Ryan or Bob, where do you guys come in on this? Do you agree that the volume of the motor basically determines how much torque the motor makes?
I mean, I agree with the point that it's the easiest one to quantify in that regard. I mean, obviously there's many factors that go into the torque that a motor produces, but when you're looking at, and it's also important, I think, to point out that modern FPV motors, anything manufactured within the last year or two, has the other factors involved are all in a fairly narrow window of performance. They're all manufactured to fairly similar specifications. Even if you take a really inexpensive motor like an Emax Eco, the first edition Emax Eco, and you compare it to a really high performance top tier motor, there is a difference. I'm not going to say that there's not, but the window of difference compared to the total window of available performance variation is smaller than you might think. So in that regard, probably if you're looking at the motor, the stator volume is going to be a very good indicator of the kind of where it sits in the torque production, kind of spectrum.
Yeah, Bob, sorry about that, guys. Bad moderator. I threw to two of you at the same time. I'll try to do better. Bob, go ahead. What were you going to say? Torque and volume.
So the volume absolutely is a very obviously important indicator. However, I have a question about how magnets work that I want to ask Ryan and Chris. And I think we should actually start from the magnets and go in, because the volume, it depends on a lot of factors. And plus, the inner area of the volume doesn't actually do anything. So like it's all bearing and shaft and everything. And so what you're really getting at is the surface area of interaction between the actual stator pole and the magnets. So by increasing the volume, of course, you're going to increase that surface area. However, as you go higher, you're going to increase that surface area a lot more. But that's not the only way. And as Chris has a very interesting theory about like the advantages of having a potentially advantage of having a shorter motor and the extra benefit you get from having just a shorter motor in various. Anyways, continue on.
So Bob, I think what you're getting at is that as the motor volume goes up, there's some part of the motor volume that is made up of the bearing and the shaft, obviously. But then the rest of it is the winding and the core. And that's going to contribute to its ability to make magnetic flux because, you more windings, more core, more magnetic flux. But then I think what you're getting at is that you've got that surface, the outer surface of the cylinder, where the stator is interacting with the magnets. I think you're saying that seems like it's more important. Chris,
so
go ahead.
I wanted to jump in on that because that's a really common, I think, a common thing that people have talked about when they've watched my video is, well, what about the volume of the bearing and the volume of the shaft? And it's really subtle, the difference. But my analysis is not the volume of the stator. It's actually the outside curved surface of the motor multiplied by its radius. Now that turns out to be 2 pi r squared. But it's not actually the volume of the copper windings or the volume of the bearing and the shaft. It's actually it's about the outer surface, which gives you the force multiplied by the radius. If you force times radius gives you the torque. So in terms of what's inside, that's actually a separate consideration. So in terms of like the amount of copper and stuff, the more copper you can fit into a motor, the better it's going to perform, all else being equal.
So, Chris, I think what you're saying, and this goes back to some of the comments that are in the chat, people talking about how you can't talk about torque without talking about the length of the lever arm. And when you talk about the length of the lever arm for a motor, it's the diameter of the motor. Therefore, it seems obvious that the diameter of the motor has to be related to the torque the motor produces. And what you show in your video is that when you take the torque formula and you take the formula for magnetic force, the terms actually just by coincidence rearrange themselves so that the resulting formula is the volume of the motor. Is that right?
I don't think it's by coincidence, right? It's actually a function of the way the physics works. And it's, if you think about it logically, it's actually expected because you're talking about the amount of force and the lever arm, right? So when you're looking at the way force is created through magnetism, there are factors that are actually the same, so they cancel each other out. So like it's actually a byproduct of the physics involved. It's not a coincidence. It's actually the way, just the way it works.
Right. Mathematical formulas always describe physical, and when the math just randomly works out a certain way, it's because the physics work out that way.
That's right.
There's something deeper at work there, isn't there?
It's important to point out, though, that that when we say that the torque a motor produces is proportional to its volume, that takes into account the fact that torque is related to the lever arm length. It just there's the volume is there.
Correct.
Yeah. Now, Chris, you said you made the argument, and this was the sort of controversial bomb you dropped in a sense that made me want to get all you guys in the same room and just make you argue with each other. But probably not going to argue. But you said that a 3-to-1 ratio of diameter to height, assuming you don't need a thinner motor, like for example, if you have a 360 cam where you need it to fit within the seam line, assuming there's no physical constraints on the size of the motor, you argued that a 3-to-1 ratio of diameter to height, like for example, a 2207, 3 times 7 is 21. That's you said that was the ideal size for a motor, and all other sizes of motors were a lie and a sham. No, you didn't go that far. Tell us more about that argument, and then I want to get into that.
So the first thing is that 3-to-1 ratio that I sort of said was for a typical, relatively lightweight 5-inch freestyle quad. So that's the first thing. And the way that I got there was by thinking, well, one of the key issues that motors have is they generate a lot of heat because there's wasted energy in the windings, and you need to get rid of that heat, because if the motor heats up, its performance will drop because the copper gets more resistive. It just dissipates more energy. The
magnets lose magnetic flux when they heat up.
Yeah, absolutely. And so given what we've talked about and the moment of inertia effect, you want the tallest motor possible that doesn't overheat. That's what you want.
You've just introduced a new concept, at least to this talk. The moment of inertia effect. Briefly, for people who didn't watch your video, talk about that.
Sure. So one of the key requirements we have for our motors is to change the rotational velocity of the prop. And in addition to the torque, the other factor that's important there is the moment of inertia of the system. And a wide motor bell that's the same mass as a tall motor bell will have much more moment of inertia. And so that torque of the motor, more of that torque is being used to try and accelerate the motor bell, less is left over to accelerate the prop. And the result is a slower rate of change of RPMs, which is
and all else being equal, it's basically acting like a flywheel.
Exactly. Exactly like a flywheel.
I think it's worth pointing out something, and I've kind of talked about this before in the past, but it's been a while. So when you're looking at the weight, though, there's an interesting thing you need to think about in terms of productive versus non-productive mass, right? Mm-hmm. So some mass actually contributes to increasing the torque of the motor. So if the contribution of that mass is greater than the moment of inertia that mass creates, then you're still getting a gain in torque.
Ryan, dive into that a little deeper. When you say some mass contributes to changing the inertia of the motor, what do you mean?
Changing the torque of the motor. So, and this goes back to Bob's earlier question, which I think is, this kind of all ties together, right? When we start thinking about the role that the magnets have, because if you add magnetic mass, that magnetic mass increases the flux that magnet is able to produce in the coils, right? So that increases the torque. So if you're adding magnetic mass to the bell, that's increasing the moment of inertia of the bell, but depending on where that mass is sitting and how much of a magnetic field increase it's creating, it's fairly likely that, it's at least contributing to the torque that the motor is producing, which may depending on where it sits, offset the increase in the moment of inertia in the bell, or may not, depending on a lot of factors. And this is a really interesting discussion, because early testing that I did on 2205 size stators showed that anything above 1.8 millimeters of thickness in the magnet was actually contributing more towards the moment of inertia than it was towards torque production. Now,
so for the purposes of kind of, because trying to simplify it down, if you've got the two bells that are the same mass, the wider one is gonna have more moment of inertia and therefore be slower to accelerate than the narrow one. So then the question is, but as you said, if you're adding mass to both bells, the extra mass you add to the wider one is going to hurt you more than if you add it to the narrow one.
Right. And
Bob,
and, you know,
Bob,
like,
I want to give Bob a chance to weigh in here because Bob, I think you were going to say something about the. I think you've said stuff in the past about the shape of the magnets and how that contributes to the motor performance. Do you have anything to contribute here?
Yeah, so no doubt. So going taller will get you more power than wider. However, heat and everything mixed into it, it's arguable, and there's a balance point somewhere. And in the 5-inch motor size, we're still talking about very small motors. Everything changes once you pass 7 inches. Like everything changes. And once you go below about 3 inches, everything changes again. So we're talking about a very narrow subset of motors. On top of that, if you look at, so if you have a paperclip and you bring a magnet close to the paperclip is attracted to the magnet because the magnet is rearranging all the electrons in that paperclip and creating a flux, turning the paperclip into a magnet to attract it to the magnet. So that's called reluctance force. If you take a magnet and then, well, if you take an electromagnet and put it next to the paperclip, the stronger the electromagnet, the more attractive the force will be. But if you take a magnet and put it next to that electromagnet, how much force can that electromagnet generate before the magnet starts acting like a paperclip? So at some point, the magnetic field of that permanent magnet will no longer matter. And the force of the electromagnet is so strong that it's overcoming the magnetic field of the permanent magnet and turning it into a stronger magnet than it ever was. Now, the trouble is that once you put this into a motor, you've got all these magnets spinning around. And even though the magnets are positive, negative, the poles are flipped, if you surpass the flux from the magnet, you're going to start inducing a magnetic field into the magnets next door. And so you can never actually overcome the flux that's being given off from the permanent magnet. So in essence, the magnets are the most important thing of the motor, and you can always generate more magnetic field from the stator core.
Sure. But
for the most
all
part,
all of those things are absolutely correct, but they don't change what the original question was about, which was that all else being equal, making the motor wider gives it more moment of inertia and therefore it's slower to accelerate.
So Chris, your argument, Chris, would be that if heating was not an issue, the need to push air through the core to cool it down and prevent degradation of performance, then the tallest, narrowest motor would give you the best response time due to moment of inertia. And that would you argue, Chris, that the main reason we flatten motors is cooling?
I would say that's a really important consideration. So for a freestyle motor where you're mostly low in the throttle and then occasionally you want that maximum power for a dynamic move, then that 3-to-1 ratio starts to make a lot of sense. If, however, you're looking at a different application, like maybe you've got a Cinewoop where you're sitting always much higher in the throttle because you've got much less thrust to weight ratio, you then need to worry about that motor getting too hot. And that's where going wider to improve the cooling and putting maybe fins on the bell like the Carrera Toa motor has, the Toa turbine, doing things like that might be what you need to do in order to keep that motor cool. But you don't just want to go wider than you need to. So you go as wide as you need to keep that motor cool and no wider.
Well, let me go over to Bob on this one, because Chris, I think there were people in your comments section. I'm not blaming you for this, but there were people in your comments section who said, finally, someone bringing some actual theory to this, which is true. You totally are bringing your knowledge is. By the way, I said I would give you a chance to say, what's your actual field? What's your title or your degree? What do you do?
Sure. Yeah. I'm an aerothermal engineer by training. So my course was basically in everything you need to know to design a jet engine. That's how I like to explain it to people. So it's fluid dynamics and thermodynamics and combustion dynamics and turbo machinery and all of that fun stuff. When I finished my course, I went and worked for an engineering consultancy for many years, and there I helped clients all over the world bring all sorts of new products and technologies into the market. Most of my clients are actually on the US West Coast, so that's why it's kind of interesting that I end up talking with you guys in the US. And now I work for a startup in Cambridge here in the UK. And that startup is making really tiny, it's the world's smallest mass flow sensor. So again, it's complex thermodynamics and fluid dynamics, but on a like sub-millimeter scale.
Yeah. And I said recently, finally, someone, our hobby has managed to just catch someone in the net who has this background to start sort of, giving more information. So I'm really happy that you're in the discussion. But I was saying, there are people in your comments who said, finally, someone with a real theoretical background and all this sort of bro science can get in a hype can get thrown out. And Bob, I feel like they were talking about you, and I felt like that was unfair because
I don't
Bob,
think it's unfair.
You're being humble, and I give you credit for that. Hang on, let me compliment you, and then I'll let you go. Your background, your training is as a dentist, true, but you have so much experience trying different things, probably more than just about anybody in the field, not to insult anybody else. And I feel like when you say, I tried 19 different motors, I flew 27 packs on each of them, and I like this one the best, you're not just talking out your butt. And you tend towards wider, flatter motors. Your 5-inch motor, I think it's approximately a 4-to-1 ratio of diameter to height, and your 1303 motors, so you tend more towards a 4 or 5-to-1 ratio. And I know you've tried motors with a 3-to-1 ratio and probably a 2-to-1 ratio. I'd like to hear from you what drove you towards those wider, flatter motors.
Yeah, so give me like a couple minutes here. So
Okay. Take your time.
I actually didn't like wider motors. I preferred taller motors. The difference is that when you change the kV, change the magnets, and things start moving around, it changes the way the motor performs. So I actually majorly prefer the 2208 over anything else. However, when you start looking at the wider, flatter motors, you can actually pack arguably more performance into a lower weight package, and you can get a performance curve that is a little different than any other taller motor. So these wider, flatter motors, you get better cooling, sure. But the thing that I primarily feel is that, first of all these motors are fast enough to give you fantastic flight control. Unless the motor is just drastically too small for the prop or the quad that you're flying, it's going to perform similarly. That's why the cheapest motor and the most expensive motor are performing very, very similar. The difference is that as the motor rotates, as the motor spins, what's really shocking is that the wider motor up at the high RPM range will give you more top end than even a similar volume taller motor or a higher volume taller motor. And that's the part that really gets me. And these wider motors, they tend to give you a throttle curve and a throttle feel that is just way more fluid in the range that me as a human needs or wants. So you felt it also. It's not something that you feel immediately. It's a little bit subconscious, but then when you start working with it, you realize, oh wait, this is way more controlled, way easier. And Chris is going to say, he's absolutely correct in saying that we should be running the objectively best motor that we can find and then doing the rest in software. That's just not quite the same.
In terms of the throttle curve, Chris made the argument that if you want a throttle curve or something, you should not be doing that with the design of the motor. You should get an ideal response from the motor, the fastest responding motor you can, and then do all your feel or curve.
Hold on, give me one more minute.
Yeah, go ahead.
So with these wider motors, there are a bunch of issues to deal with, and I've worked those out. And clearly, with the most recent motor, the manufacturers have screwed up, and they didn't really respect the wishes that I had of the final product, and they switched everything up for the final product. With these wider motors, you can actually reach a point where you've optimized all the numbers, the kV, with the magnets, with the stator, with everything. With the taller motors, you reach a point where the motor can keep going if it didn't heat up, if it had magnets, if it had all this other stuff. But these wider motors, you don't really get as much heat if everything is tuned correctly. And you can tune the magnet thickness really nicely. and you can actually reach the kV point to optimize everything about the motor. So it's really more of, you can optimize a specific size motor easier if all the other stuff is taken care of. Whereas taller, bigger magnet, everything, it's better, but it's more difficult to get to the point where, okay, now your heat's okay. Now your kV, is it enough? Now your magnets, are they good? Do you need thicker? We don't know. So it's more of a matter of like the ingredients that you use are more manageable than just having all the ingredients available to you.
And it's easy. It really brings up the point you made about your 5-inch motors and the problems you had. For those of you who may not know, Bob, you got this 5-inch motor that you designed, and it's supposed to be really, really amazing. I've flown it. I do think it has some unique flight characteristics, which is saying a lot, because most motors, I fly them and I go, yeah, it feels like a motor. I don't really care.
Right.
But then you sent them to manufacturing, and they made some slight changes that they probably didn't think it was going to matter. They were probably trying to save a little money, and now the motors are desyncing. And the ability to sort of tweak and design a motor to get the characteristics you want through actual manufacturing, I think that's the point you might be making, is that these motors are easier to make them fly the way you want. Ryan, as someone who's tested a lot of motors that have been manufactured, what do you think about that?
Yeah, I mean, I'm going to disagree with one thing Bob said in particular. He said that the wider motors will give you more top end. And in all of my testing, 300 plus motors, I have never seen that to be true, not once.
Yeah.
So like that's in terms of RPMs, like you're going to hit higher RPMs with a taller motor, period. Like the wider motors have a flatter curve. Like they hit higher RPMs first, and then they taper off as you get to the top compared to a taller motor. Like universally, that is true. Now, you might make the argument that difference is much less in an unloaded, non-static environment.
Right, because all your testing is done on the bench.
But it's never going to be the other way around. Like you're never going to get more RPMs out of a wider motor unless it's actually more stator volume or has stronger magnets or a smaller air gap.
Why is that, Ryan?
You know, all the other factors that go with that. But
if Chris is, sorry, Ryan, I'm going to interrupt you. If Chris's claim is that the volume of the motor controls the torque, end of story, then why does a taller motor give you more RPM at the top end?
Well, I don't think Chris said that. I don't think he ever said that was end of story. I think he said that was just an easily quantifiable way of.
All right, that's fair. That's fair.
So there are certainly plenty of other factors that you can change that have a big impact on the torque of the motor. It's just those, and as I mentioned earlier in our discussion, those factors are all in a small enough margin of variation that they don't play typically significant factors in the overall variance, right? And they're not something that you can look at a motor's label and tell from reading the label, right? They don't publish what the air gap is between the stator. They don't publish how thick the magnets are. They don't publish, a lot of these factors that have an impact on torque. So they're not something you can ever know. And even then, as Bob knows, those may change between batches. Like you may have a batch with 1.8 millimeter magnets and the next batch may have 1.6 millimeter magnets. Like
awful.
These are just things that you can't really easily quantify in a motor. Now, if you are doing what Bob does and specifying very specific things from the factory in sample runs, you're going to be able to control those variables. And so things like the air gap between the magnets and the stator, the thickness of the magnets, the rating of the magnets, which we can talk about as well, being like the N52H magnet that everybody runs is completely bogus, but like the actual rating of the magnets doesn't really matter. What matters is the relative strength between the magnets, right? So if you have one that's relatively stronger than the other, and that's what you're getting by reading that label, right? If somebody says N52H, it means they're using a relatively high field strength magnet, whether it's actually N52H rating or N55SH, which doesn't actually exist, or that doesn't matter as much. What matters is the relative strength rating. But the point is that all of those factors play a role in the torque production. So the only way you're going to get high RPMs, and it's really important to understand how the physics works, and Chris can chip in more on this. This is his wheelhouse, but the faster you go, the more torque load on the motor you're going to get. So the higher the RPMs go, the more the torque matters. Because you're going to be able to push higher and higher RPMs, the more torque that motor has, assuming everything else is constant, like, your prop pitch, the specific prop, and assuming the prop isn't deforming and flattening out, and the material isn't flattening out. But
Is it okay if I jump in and pick up something that I thought was really interesting? So the air gap thing you mentioned is another important consideration. How much that air gap changes as the motor changes RPMs. I mean, if you know, the reason we outrun our motors is because we can have a super tight air gap, and then as the motor spins faster, the gap gets wider. So that can matter too. I mean, something that I've considered is, you know, how much does that air gap change between 0 RPM and you know, 100% full throttle? You'd expect for a wider motor, you might expect that air gap to open a bit more. And I don't know what effect that would have, but it's something to consider, I guess.
And that's going to depend a lot on the modulus of the material being used in the bell and how much material is used in the bell, and you know, the specific design of the bell is going to have a big impact on that. And that's why, you know, I think like when those Emax RS2205 motors first came out, they blew our minds, right? Because there was nothing like that had ever existed. The air gap was insanely tight. They were using higher strength magnets than we had ever seen before. And based on my testing, I do believe those were actually one of the few motors that actually used N52 magnets, because they actually tend to demagnetize under high temperature, which is a common problem under the higher rated magnets. So but those things were bonkers. And I think because of their bell design being that complete unibody top bell with the forced air, with the forced air cooling, had very little flex, and they were 2205s, right? So that air gap was tiny, and it stayed very consistent under high RPM. So that was the first motor I'd ever seen that could put out like 1,200 grams of thrust. Like, it just blew my mind on a 5-inch prop. So like now, obviously that seems tiny, right? But if you think about from a 2205 motor, the closest thing up until that point was the Cobras that were 2204, actually 2205.
Right. I remember that.
They were putting out, 900 a kilogram of thrust, and we thought they were super powerful. So, like jumping up by 300 grams on a new release was quite remarkable. But yeah, I think all of those things obviously play a role.
I also wanted to talk a little bit about feel, because I think feel is something that's super important to people when they choose motors and props and the combination of them. And a lot of people have talked about, pilots sometimes say that, a 2306 motor versus a 2207 has more low-end resolution and more low-end feel.
Yep.
And I think that can often come about because a 2306 is actually about 6 or 7% smaller than a 2207. And if you think about, when you're moving the stick, if you move the stick the same amount, but you get 6 or 7% less change in thrust, that feels like more resolution. That is more resolution. So if you pick a tall, big motor like a 2208, or even I know Joshua, you favor a 2408, that you might lose some of that resolution, because even a small movement of the sticks is a much bigger change in thrust output. And I think that to kind of fix that, or to address that, people should really be considering using throttle expo, even throttle limits. Racers use throttle limits a lot, right, to give them that resolution and control. So that could be something that I think more of us should be doing.
I'm going to disagree with that to a certain extent, and I'll tell you why. Because when you fix it in the flight controller, when you fix it in the radio, there's still a fixed number of steps that the flight controller can send to the ESC in order to make changes in the throttle. So by putting a throttle cap on there, you're actually reducing resolution significantly between the flight controller and the ESC, because it only has 2048 steps. So you're reducing the number of steps that can be sent. And then you have, I think, a good way of thinking about the effective resolution of a particular motor design, a lower torque motor, or something like that, or even if you just reduce kV, which I think is actually the best solution, which we'll get there. So you have to think of it in terms of PWM duty cycle, the amount of steps that duty cycle is broken into, and how much thrust is changed per step, effective throttle step. So there's a couple of factors when it comes to resolution there. So you can get some of that low throttle resolution back on a more powerful motor by simply dropping KV. So that's going to be, in my mind, that's going to be the most effective way of getting high response rates, but increasing the, you still maintain that high torque, but you're decreasing the KV, which is effectively changing the throttle resolution at the ESC.
I mean, that's a really interesting question. I would be interested to ask sort of people how much resolution they think they have in their fingertips, because I know as a pilot, I don't have 2048 steps.
But it doesn't just change at your fingertips, right? It changes.
Bob wants to jump in.
Yeah, Bob, what do you got?
So 2048 steps is ridiculous. Chris is right. There's no human that could tell the difference between that. What you're doing by reducing your throttle limit, and particularly the percentage output of the controller. So if the flight controller wants, it can go farther than whatever your fingers are doing. Right. So what I found is that you can take a motor that has more KV on it, which will arguably produce more torque and thrust and more ability for whatever the flight controller wants to do with it. And if you limit your throttle down just 10-15%, you can hit max throttle. And, well, first of all, the spread of that entire control is spread across your throttle stick. Like it's a wider spread on the stick, as in you can't reach the top end. But if you're maxed out on a quad versus accelerating on a quad, the amp draw at max is way less than an acceleration. So once you reach max throttle on your stick, the quad is still accelerating. So you now have access to pretty much the same top end, but it just takes longer to get there, and your throttle stick, it does less when you move the stick. So you now
I think that's the key, right? Which is that you can be more precise, because the same movement of the stick is a smaller change in thrust. And that you can also achieve that with Expo as well, which is if you don't want to limit yourself and you do want to use all the power, a bit of Expo might be the way to go. And I think, we're very familiar with Expo with our rates, with our sticks. It seems natural that we could use the same approach with throttle to get more fine resolution down at the low end.
I am going to disagree with Bob on the fact that 2048 is not feelable. And I have had some very, very good conversations with some of the world's best freestyle pilots, to the point where 2048 is actually not even enough. And the fact that they can feel effective throttle
can
resolution.
They though? Ryan, I'm gonna call you though. I mean, can they call? Because people in Chris's chat were saying, oh, bro science, you think you can feel the difference, you're not really being scientific. Are you being scientific? I mean,
let me finish.
Or did they just say, I think I need more resolution?
No, this is the pilot that I've had the most discussions with is Damien Gans, Blackbird FPV. I've had a lot of really detailed discussions with him about how the different settings that we do impact flight feel. And he's a little bit far off the deep end, and you have to kind of filter what he says through some additional understanding. But I will say that in a blind test, he can tell the difference between an ESC that is running like D-Shot 2400 versus D-Shot 1200. And I struggled for a really long time to understand why he could feel the difference. And he can do it every time, 100% of the time. He can feel the difference. And even if he doesn't know, you do the test, you check the settings, he nails it. He can feel the difference. So I mean, in a double blind, fully blind test, he can feel the difference. But
hang on one second. The difference is that, go ahead, Ryan.
The reason why he can feel the difference is because of dithering, right? So it's increasing the effective throttle resolution of the ESC. So you're getting, because of the way it's sending the command to the ESC, you're basically, like, the motor can't respond any faster. It has nothing to do with motor response. What it has to do with is the dithering in the throttle signal between the flight controller and the ESC, and increasing the effective resolution of the steps in the throttle. And that's what he's feeling. And it took me a while to come to that. So that tells me that there are at least some pilots out there who can feel the difference in throttle resolution at a very, very fine detail.
Bob, go ahead. You want to jump into something?
So first of all, I'm a dentist, so a tenth of a millimeter to me is actually a lot. If your throttle stick moves 4 centimeters, which is a lot for a throttle stick, that is 0.0019 centimeters. So you're telling me somebody
depends on the length of your sticks too.
Let's say the stick is 10 centimeters of movement, which no stick in the world will ever be. 10 centimeters. 10, 1,000.
You're talking about from zero throttle to full throttle, the sort of length of the throw.
It's like you're talking about movements that are less than a tenth of a millimeter, which I can actually feel as a dentist working in the mouth, but it's not the same as flying on a thing.
Well, I want to say that I think there's truth on both sides. How many people out there are flying with a ratcheted throttle right now? Because they didn't know there was an option to have a smooth throttle. If you have a ratcheted throttle, you have about, I don't know, like 100, 150 steps of resolution maybe, and you can still fly a quad with a ratcheted throttle. You could do it. Obviously, smooth is better. So
and I also think that it's important to note that throttle resolution doesn't just impact you controlling the throttle. It also impacts how the PID controller controls the throttle.
Well, not if you just reduce the throttle output.
Yeah,
Right.
It doesn't change it if the if you don't
we're talking
limit
about
it in
throttle versus motor output resolution.
Right.
And I'm talking specifically about the resolution of the throttle between the flight controller and the ESC. Like that's specifically what I'm talking about.
That doesn't change.
It does if you're dithering, though. That's what I'm saying.
Well, yeah, but if you're just reducing the throttle, the maximum control throttle, it's not going to change anything between the flight controller and the ESC.
Yeah, it's actually another advantage is that you know if you want to feel where you don't have too much power, you want something that's super smooth, but you still want to give the flight controller all of the responsiveness and control that you can possibly give it to stabilize the quad against wind or turbulence or whatever. Then a throttle limit is a way you can kind of try and get a bit of the best of both worlds, where you have really gentle throttle response, but the flight controller has all the juice in the world to keep you stable.
Yep.
Let me throw out a scenario here. We've talked about control and resolution, and that a lot of what people think of as throttle curve in a motor might actually just be a difference in torque production. Let's think about 3 ways that we could reduce or increase the response and torque of a motor. One would be to use a larger motor. A motor with more volume will make more torque. One would be to use a motor of the same volume but a higher kV. It will make more RPM.
Per step.
And one would be to use a throttle curve in your controller or something to simply change the output that you're commanding from the motor.
Like thrust linear.
What are the differences going to be between those 3 scenarios from the pilot's perspective? Who wants to dive in first?
Well, I would say that any software change that you make, so thrust linear, that sort of thing, is not fundamentally increasing or the ability of that motor to control the prop. You might be telling the motor, pushing the motor to accelerate, telling it go faster, and it's just going, I can't accelerate any faster because this is just the maximum mechanical torque that I've got. So that's probably not the way I would go if you're looking to improve responsiveness and you believe that the motor is the limit. In terms of bigger volume motor, obviously some trade-offs there. It's going to be heavier. And what was the third one you said, Joshua?
KV. I mean, we changed the motor RPM by changing the KV as well. So we could just go to a lower KV motor, or we could go to a smaller motor that's going to be less responsive.
So KV, again, won't change the maximum mechanical torque that the motor can create. Now, the question there is, are you interested in low throttle responsiveness or high throttle responsiveness? I would say typically in freestyle, we most care about low throttle responsiveness because it's at low throttle that we have some of the worst inlet conditions on our quads. We're like falling through the air's going backwards through the prop. It's like the worst possible inflow conditions. that low throttle responsiveness, you might actually see a small improvement with lower kV because of a reason called joule losses. When we think of our system, quadcopter, we've got the battery, we've got the ESC, we've got the motor. A high kV motor can make the same torque as a low kV motor, but it needs a lot more current to do it. Now, in an ideal world, that motor can draw the extra current that it needs. But when it draws that extra current, you get more losses in the battery, you get more losses in the ESC, in the cables. And so what that means is that a high kV motor can actually be making less torque at low RPMs than a low kV motor because of the voltage drop in the battery and the ESC and the cables. And so if you really want low throttle responsiveness as a pilot, like a freestyle pilot, I would say, don't overdo the kV. Make sure that you keep your kV moderate. Going very high on the kV, you might actually reduce the maximum torque that the motor can make at low throttle.
Bob, I saw you nodding along when Chris said that if you want low throttle responsiveness, use lower kV. What were you thinking?
Well, yeah. So a lot of people ask, like, can I take a 2400 kV motor, limit the throttle, and run it on 6S? And yeah, you can, but it feels very different. And so you want, as far as my testing has gone, you want a little bit more kV than you need, just so you can do a little bit of a throttle limit, give you the resolution, but not limit the torque from the low end, which is everything that I work for, like everything. And I don't know how the motor, like the size and width and all this stuff, is actually functioning on the low end. But as you felt yourself, the wider motors with the appropriate magnets have more of a meaty and smooth feel and controllable feel on the low half.
I wonder about that. I've been thinking about that for this whole conversation, Bob. I absolutely do think that your motor, your 5-inch motor, has better low end control than the other motors I was flying, the 2306, the 2207s.
And you haven't felt the real one. The real ones are different.
And I've wondered if maybe there's some that freestyle pilots and specifically are more aware of torque or resolution at the low end, just because let's say you're trying to hover or you're trying to hit a gap. If your throttle is off by a small percent, you're going to miss the gap. You're going to hit the ground. Whereas when I go to 75% throttle or 85% throttle, chances are I'm not trying to like hit a gap at that. I won't notice if I'm off by a few percent. I wonder if we're just more sensitive to changes in resolution and torque at low or mid throttle, because that's where we care most about the precision.
Yeah, freestyle pilots, we put our quads in the absolute worst aerodynamic conditions that you could ever think of. We hurl the thing backwards at high speed through its own prop wash, and we're like, no, the video has to be perfectly stable. It cannot move an inch. It has to be smooth. And in that situation, we're asking a lot of the flight controller to keep everything stable in horrible conditions, horrible inflow conditions. And so, I mean, Bob's motor will have a lot of low-end control because I understand it's a really big motor. It's a huge motor, right, for a 5-inch prop. Massive.
No, it's not that big.
Isn't it?
Well,
Isn't
Bob, you've resisted giving out the exact dimensions to help keep people from cloning it.
Yeah. Does it have more volume than a 2208 or a 2207?
No, it has less volume than a 2208.
Okay, less than a
2207.
Yeah,
but more than a somewhat.
2207.
Okay,
it's around 2207.
It's in the ballpark stator volume wise to a 2207.5. Like that's roughly where the stator volume is.
So that's a really pretty big motor. So we would expect that motor to have really good low throttle control because it's got bags of torque.
Yeah. Well, my take on it is that you're dealing with a bunch of different factors here. So you have the torque, but then you also have the moment of inertia of the bell of the prop or the bell of the motor, which is changing the relationship to how it accelerates, how it decelerates.
Right.
You've got the relationship between the specific, magnet thickness and magnet dimensions and the lever arm and all of that stuff playing together. So, I mean, I absolutely think that messing with all those variables is going to functionally change the shape of the throttle curve, the way it accelerates the prop. And we were talking about smoothness is exactly the opposite of torque, right? Like torque, lots of torque means not smooth because it's changing things very, very quickly. So
that's why for a while freestyle pilots would use N48 magnets. They don't anymore. And the weaker magnets were smoother.
You say they don't anymore. But you have to remember that magnet ratings listed on these things are not reality.
Fair enough.
So I can tell you for a fact that a lot of the popular freestyle motors are still using N48 and N50 magnets.
All right, I got to pause this here for a minute. We've been going for about an hour. I got a bunch of super chats I'm going to read, and then I'm going to address Huff19's comment about Zing cloning Bob's motor. But let me get these super chats. Thank you guys for being patient. Obviously, this is such a great conversation. I didn't want to interrupt it every time there was a super chat. But Yarrow S, thanks for 10 Norwegian kroner. James Hu, thank you for £5. He says, Bob, please stock crest strips. We can't get them over here. Can't get crest strips outside the USA. They think if you stock them, I don't know. Thank you for a super chat, James. Yeah, James is in the UK. RC Ritter FPV, thanks for a $20 super chat. Thanks for everything you guys do for the hobby. Crap, kids are home. Sorry for the ramblings. Disco Volante, thanks for €10.99. Just great talk. Thank you. Todd Tube, thanks for $5. My head just exploded. King Sloth, thanks for 50 Norwegian kroner. Pro tip, decreasing KV. Listen up, guys. Decreasing KV also significantly increases efficiency or thrust. We'll see if you guys think that's true in just a minute. Aber the Ham, thanks for $5. I think Chris is looking into this. So feel free to leave this can of worms closed. But motor notchiness, does it make a quad more difficult to tune? We'll get those in just a second. Huff19 says, too late, Zing cloned Bob's motor. Zing does have a motor similar in size, the Zing 2 2806, I think. However, it's not in the same KV. Bob, I asked you, I said, hey, did Zing clone your motor? And you said, the KV's going to make a difference. So I don't know if you want to mention that.
So here's the thing about cloning. So over the years, the industry has improved all the technical knowledge that they have. So you're not going to get an Acura NSX and expect it to be a Ferrari. Like a Ferrari is different than an Acura NSX, but the NSX might perform very similarly, but it's just not the same. So as like these conversations are fantastic because people are starting to realize that, okay, well, there is a difference between all these products, even though the cheapest one and the most expensive one will ultimately fly, they all work properly. But once you get past the, okay, now I've built every single quad, I'm looking for more performance, I'm looking for whatever, then you can start looking at the more tailored motors. And not all of them are appropriately tailored. A lot of them are just motors that the manufacturer makes that they just rebrand. But something that somebody has distinctively gone through and tested multiple different options and come up and found that, no, this one is the one that they prefer, that's now a motor that's a little bit different. And it's, while somebody else might clone it, try to get the same size, whatever, it's still not going to be the same motor because of all the factors that go into it.
Yeah, I think...
All that being said, the motor is a 2506. It's not that hard to measure. And iFlight, I don't know if they copied it or I don't know if they copied all my other motors, as has T-Motor and other companies. But it's not an uncommon size. It's just a size that hasn't been tried so much.
I think if anybody in the world has the right to say, you could copy the size of my motor and the KV, but I've worked with a manufacturer to refine every tiny detail of this motor to my specifications. I think if anybody in the world has earned the right to make that claim, it's probably you, Bob. I'm sure your OEMs hate you for how much you make them work.
Anyway. They're not that happy.
Chris,
and that's why they end up changing stuff, right? Because his details are so specific, and then they're like, but.
These are the actual motors from the final prototype. This is the final prototype from Brother Hobby. These windings are totally different. These magnets are totally different than the actual belt. Like, even just looking on this crappy camera, you can tell that the magnets are different.
Not the
between
same.
the two. Like they're clearly not the same damn thing. And it's like, what did you think that was going to happen? Like, and the windings on the final motor are totally different than these windings. Like the quality of the materials used changed drastically.
Yeah.
Like, what am I supposed to do?
I've had that similar issue in the day job, where you have an A and a B team, and when you're doing the R&D, you get the A team, and then when it goes into production, it gets handed over, and it's no longer the R&D guys who are building your stuff; it's the production guys. And sometimes there are changes. Sometimes it gets better, but often it also gets worse.
Chris, let's talk about this super chat from Aber the Ham. Digging into the from Kingsloth, digging into the relationship between KV and efficiency. We haven't talked about efficiency a lot. What happens to efficiency as KV changes?
Well, I mean, if you reduce KV, the current required for the torque that you need to make goes down. And because all of the heating in the quad is current related, it's I squared R heating, and the heating in the battery, same I squared R, you do get modest improvement in efficiency from reducing KV. And I would say, that's important to remember, but it's also important to remember that a freestyle quad is not an efficient machine.
Oh God, no.
So actually, a lot of the decisions that we make about freestyle quads, particularly in our choice of prop, for example, these very low pitched props, we purposefully give up a lot of efficiency in our designs in order to achieve other benefits that we think are more important, like responsiveness and control. But if you're in really after like a long range cruiser, and you really need every little bit of efficiency, and perhaps you're also running off like a lithium ion battery where you have to keep the current down, then low KV is definitely the way to go to achieve that.
One of the things that people mistake when they talk about efficiency is when engineers talk about efficiency, they mean grams of thrust per watt of power. But when freestyle pilots and just regular people talk about efficiency, they usually mean longer flight time. So there are scenarios where you can have just a weaker motor that makes less thrust, and so you get longer flight time. It's like saying it doesn't always mean that the motor is more efficient in terms of grams per watt, though. Although it may. What about notchiness, Ryan?
Yeah,
Ryan, and what about notchiness? Or do you want to weigh in on that last one?
Yeah, the notchiness is actually something called cogging torque, and it has to do with the relationship between the stators and the spacing of the stator arms and the spacing of the magnets to each other. And someone else that actually I saw in the chat had asked about the notched magnets that iFlight is doing. And that notch in the magnets is an attempt to minimize cogging torque. However, based on what I have seen, it's not in the right place and it's not designed in the right way to actually effectively reduce cogging torque. So
But at least they're trying.
Yeah,
at least
they're trying. But I mean, I think that, I mean, I haven't seen the FEA analysis of that, so it's possible that there's a, I haven't seen the analysis, but based on my initial look at it, I don't think it's in the right place. But
where's the notch?
It's right dead center in the magnet, like right through the dead center of the magnet. Like,
oh, as in it's a slot? Like
yeah,
it's
a slot. Yeah. Like typically they would be offset in order to, and it would have to be offset in a very particular way in relation to the specific spacing of the stator arms, so that as it's crossing the stator arm at the point where it's creating that cogging torque, that it's reducing the effective field strength at exactly the right moment. So, but cogging torque can be a problem, but it's not always a problem. It depends on a lot of factors. And from what I have seen, it's the most problematic from a tuning perspective in micromotors. And I really think this is a big reason why Bob's 2203 and 1303 motors are super popular, because they change the relationship between the stator arm and the spacing of the magnets in a way that really minimizes that cogging torque. And cogging torque, especially on a really low mass bell, like micromagnets, has a huge impact on the actual smoothness of how that motor runs at RPMs. Bigger motors, not as much of an issue. Like you can have a really coggy 2207 that flies super smooth, not a problem. But for the most part, there are ways of reducing cogging torque, and I've talked to Bob about some of them. We've looked at some of the ways that might be done. The problem is that the expense of manufacturing a motor that uses the techniques that reduce cogging torque is more expensive than the benefit you get from making it. So no manufacturer that I have ever approached with any of the techniques at reducing cogging torque has been willing to actually put in the changes in their machining process, the changes in their assembly process that it would take to actually implement this. So you can use skewed magnets, you can use skewed stators, you can do all kinds of these things that are very effective at actually reducing cogging torque and then increasing the average torque of the motor. Part of the problem is some of these manufacturing engineers don't really understand the relationship between all of this, because the peak torque is actually reduced when you use a lot of these techniques. So they look at this and they say, oh, it's a lower torque motor, but the average torque is actually boosted. So you end up with a higher average torque, but a lower peak torque, which can be confusing for some manufacturers. But that's
Ciati's in the chat. Ciati is one of the proponents that Ciati flies mostly micro motors. A lot of micro, I don't know about mostly. And he's been a big proponent that Nachi motors tune harder on micros. Ciati says, Crunk, are you listening to this? Crunk disagrees with him. Crunk is also a very experienced student. Do you believe me now that Ryan is saying it? Bob, we were talking about your motors, and Ryan said he thought that one of the reasons your micro motors were popular is because they reduced the cogging torque. Do you have any comment about that?
I mean, no comment. I just test a bunch of stuff and I find the one that works. But something that's really interesting about that particular comment is that so Cinewatt motors, they are typically 15.0 whatever or 16.0 whatever. The 16.08 Cinewatt motor has like 40% more volume than the 2203, but literally everything about the 2203 is better than the 16.08. However, I don't think that's because of the cogging torque. I think that's a minor.
Yeah, I think it's probably mostly heat issues at that point, because you're running a massive motor with no heat dissipation, and it's just like the way you run a motor on a sine whoop is completely different from the way we run them on a freestyle quad, and they're so heavy, so that motor is running constantly at like 60-70% throttle. I mean, not like constantly, but it's probably spends most of its time above 50% throttle. And I'll tell you, in the hundreds of bench tests that I've done, the difference between when that motor first spins up and is cool, and you can literally watch the thrust drop off as the heat saturates the stator. I mean, it's just like, and
when
I will say that it's actually not the magnets that you're worried about, because the magnets are spinning so fast, they're actively being cooled. It's the stator itself and the copper in the stator, the coils that are heating up so much that the resistance is increasing. And like, it literally, you're talking about 150 grams of thrust difference between a cold motor and a hot motor.
And as it gets hotter and it makes less thrust, you drive it harder, and then it gets hotter.
Now the savior to that is actually voltage sag, right? So you get voltage sag in the battery and it can't maintain the RPMs, which then eventually kind of equalizes to a point where everything balances out. And again, going back to this discussion, I think that's a really critical component. And I think that's a big reason why some of these motors work better, even though they may not seem to work better, is because they're reaching that equilibrium at a different point, right? So the relationship between where the voltage sag kind of hits that and where the cooling and everything balances out to an equilibrium point is going to be very different based on the physical dimensions of the motor and a lot of these other properties that are being involved.
Going back to the question about cogging torque, Abraham followed up in the Discord server. He says, my thought is that magnetic cogging that you feel with the motor in the off state ceases to exist once the coils are powered up and electromagnets are driving the bell. So why is cogging still relevant even after the motor's being driven?
So that's largely true, but cogging torque is a thing still, even when the motor is spinning, but not to the same degree, right? So like the cogginess that you feel when you spin it is not going to be, you're not going to get that level of cogginess, but there is absolutely fluctuations in the torque as the motor is moving past the different phases, because you have to remember the way a brushless motor works, only one phase at a time is actually active, right? Well, you have one coming on, one going off, and one active. So the ones that are kind of in the off position, you have one that's actually reading the what they call back EMF, to know when the motor needs to be fired next. So as the motor is spinning in those non-active phases, you're going to get fluctuations in the torque as it's passing the stator arms. So yes, it's not the same as when you spin it fully, and it's definitely largely reduced during active spinning, especially on a motor that has a high mass bell, right, relative to the torque of the motor. So the momentum, the moment of the bell is going to have a big impact on how much the cogging torque actually gets back into torque fluctuations. But you can actually graph that, and you can see graphs of the torque fluctuations that show you your kind of minimum and maximum and mean values for torque. And that's where that cogging torque starts to play a role.
All right, I want to go back. We were talking previously about throttle curve and response curve, and I think why is there a curve in the response of the motor? Why, in other words, why is the RPM that the motor makes not just linear? Or maybe the thrust that the motor makes, not just linear with the throttle position. Chris, let me throw this to you first, and then everybody can jump in. Physics! Oh, physics is making Ryan drop his microphone. Go ahead, Chris.
Mic drop.
Why is there a curve at all?
Well, I mean, the relationship is non-linear because of the way that the torque that you have to turn the prop affects its RPMs, and the relationship between the thrust that the prop generates and the RPMs, and that so you can see that if you look at the results on mini quad test bench, that you don't see a nice kind of linear shape. You do get a curve. I mean, it's going to be an aerodynamic effect of the prop, and I don't want to say too much more because I feel like I'm maybe not the expert on this particular subject. So I'll hand over to maybe either Bob or Ryan if they want to carry on from there.
I mean, and I actually do think that, Chris, you probably are an expert on this particular area because it's related to fluid dynamics, right? And the compressibility of air. So the harder you're pushing against the air, the more it's going to compress that air and the harder it's going to push back. So as the prop is spinning at higher and higher RPMs, the harder it has to work to make a change, right? The harder it has to work to push that air through. So like the reason why you don't get the same change in thrust at low throttle with the same change in duty cycle is just because of it has to do with the fluid dynamics of air in the propeller.
So is it always going to be true then that the motor is going to be more responsive at lower throttle because it can make the torque that it creates will have a larger effect on the prop at lower throttle than at higher throttle?
Absolutely, and that's because of a phenomenon called torque reserve. So if you're trying to accelerate a prop, it's not about the torque that the motor makes, it's about the torque the motor's got left. So if you're spinning a prop at a certain RPM, some of the torque of the motor's being used to do that. If you then command the motor to accelerate as fast as it can, all it's got is whatever's left that it's not currently using. And obviously at a lower RPM, motor's using less of its torque. It's got more in reserve, and that torque reserve on the moment of inertia of the proper motor is what's going to accelerate it.
There's a caveat to that in terms of the amount of thrust generated per change in RPMs at low throttle is actually less than the amount of thrust change per RPM change at higher throttle. Like as you go higher, like there's a exponential relationship between RPMs and thrust. As you go higher and higher RPMs, the higher RPMs you go, that relationship changes.
Well,
so quadratic relationship, right? With
quadratic. Yep.
I'm not sure I follow that, Ryan. Are you saying you get less thrust at higher RPM per change in RPM?
More. So it's quadratic.
Right.
So if you double the RPMs, you get 4 times the.
Oh, okay.
Yeah.
So although the motor is less able to change the RPM at high RPM, it is making more thrust, and in some sense that's going to cancel out.
Well,
perhaps?
It does. I mean, it doesn't fully. You'll see, if you look at the slope, it goes. It's kind of like it starts low and then then it tapers off as you get higher and higher. So because of the air resistance, because of that, it's struggling to change the RPMs. And again, it has to do with that fact that like it's pushing, the more it spins, the more it's pushing back, right? So like, and that's why there's a quadratic relationship between RPMs and thrust, but it's also why it's having a harder and harder time as it gets higher and higher RPMs.
Interesting.
Bob,
go ahead.
I've got a question actually for Chris. So when electric cars started becoming popular years ago, even people would say, "Oh, they're so amazing because they have all the torque at 0 RPM." But in any car, or I mean, a car's a bad example; it's so complicated. But in these little simple motors, even just spinning them up, I feel like you get more torque after the initial inertia of the bell spin starts. Is this true, or is the maximum torque actually at 0 RPM?
Chris, you want me to take this one? I have some input on it, but if you want,
Chris, go first.
Please go ahead. I think we're going to agree anyway, so you go ahead.
So the issue that we're having in this regard isn't related to the motor; it's actually related to the electronics that drive the motor.
Yeah.
So
the ESC.
Right.
Yeah.
We are using non-censored ESCs. So the torque that they are capable of producing at low RPMs is extremely limited because the motor has to already be in motion for them to create torque. So
past that point.
They're basically guessing up until a certain point. So we can't generate the full torque the motor is capable of doing at 0 RPMs because we're using non-censored motors. If we were using censored motors, we would have massive amounts of torque at very low throttle because, again, as Chris said, the reserve torque is so high. So yes, you can generate huge amounts of torque with an electric motor at very low throttle, but we can't because we are not using censored motors. Now, that comes with a caveat. There is still a torque curve, and the peak torque output of a motor is still around 50% duty cycle. But again, that has a lot to do with how we're driving the motors, even with a censored motor, than it does with the physics of the motor itself. It has to do with the way FETs work and the way they switch on and off and things like that. But Chris, if you have anything else to add.
Well, my only comment was that when people talk about electric cars, they're comparing electric motors to internal combustion engines, and internal combustion engines really struggle to generate a lot of torque at very low RPMs. And that's just because the way that they create that torque is just so totally different from how an electric motor does. So compared to an internal combustion engine, an electric motor has, censored electric motor has just enormous amounts of torque. The torque of an internal combustion engine peaks at much higher RPMs. So it has a much steeper increase with RPMs. Electric motor, you get a lot at low RPMs with an electric motor.
Wrong Way FPV in the chat says, how hard would it be to make our motors censored? And Wrong Way, I think there's a little bit of flawed thinking there because a mini quad doesn't really need torque down low because our motors are never stopped. Right. Like a car, you want to be able to stop the motor and run it slowly while still generating torque.
It's called loaded start.
Yeah.
We don't
Whereas mini quads, once the motor's spinning, you hope to God it never stops, and you don't need torque down low. So there's no motivation to make a censored motor.
The caveat to that is the super large multi-rotors, right? Like 30-inch props, 20-inch props. Those are almost universally already censored motors. And there was a company producing censored motors even for, I think they were shooting for 6-inch props. I don't know that it ever took off, but they were working on them. They had produced them. But the truth is that it requires a completely different drive methodology too. So you're not just changing the sensor on the motor, you have to make a speed controller that utilizes that sensor. And then that opens up all kinds of wonderful things like
vector control.
Yes, I'm trying to remember the acronym for it, but the basically vector controlled ESCs. So like VESC is an open source project that actually uses that. So there are VESCs and we could use censored motors and it's definitely a thing. But the benefit of that would actually be that we would probably have a lot fewer fried ESCs and fried motors because when the prop was blocked, the motor would simply know it was blocked and just stop pushing, right? So like, your turtle mode would be a lot safer because
actually, you could get out of a tree way
Right.
easier.
Right.
Because you could just slowly move the prop and push yourself out of the tree.
Absolutely. So
Yeah.
there would be benefits to it, but they would be, they would be, I think that the benefits would outweigh any of the costs that would be in,
the cost.
or the cost would outweigh any of the benefits that you would get.
I want to go back to the concept of torque reserve. I think if there's one concept that has come out of, for me at least, come out of this discussion and Chris's videos, it has been the concept of torque reserve. And it's something that I think people who work with motors maybe think about intuitively, but haven't sort of codified that that's one of the most important specs to think about when you're thinking about how a motor is going to perform. The question that I have is, if you had infinite current, then would the motor have infinite torque reserve? And obviously that's not realistic, but why would it not? It seems like if you want to make more torque, just have more current and you make more torque.
Well, current is
Why
a
is that
pull,
not true?
right? Not a push. So like the motor will only ever use as much torque as it's demanded to have. So at some point, the torque that it's asking for is going to exceed the physical limitations of the motor. Like the windings will just have so much heat in them that they will burn out. So that's really your limit of even if you had an infinite torque or an infinite current supply to the motor, it has physical limitations on how much torque it can produce simply because of how much energy it can absorb before it completely melts, and
also the maximum field strength that you can generate in that air gap. I mean, at some point, just putting more current in the electromagnet is not going to give you more useful field strength in that air gap.
It's actually,
you'll start like demagnetizing your permanent magnets.
It's actually a rating on the motors, right? It's called stall torque. So there's a particular torque point where the motor will no longer draw beyond that point, and the motor will just completely stall. Now the stall torque, again, like I said, it will melt the motor if it stays stalled for even a couple of milliseconds. It'll just. But the stall torque of the motor is the actual physical limit of how much torque that motor can provide. And since torque and current are directly proportional, that also is the maximum current that motor will ever draw.
So do you feel that, like, if you think about a motor we want the motor to generate torque, and now we've got two potential limitations. The motor simply could be at its limit of the ability to generate torque, or the motor could be current limited. The battery, there's too much voltage drop in the lines. Where are we in mini quads? What's limiting our performance? Is it the motor, or is it the ability to provide current?
Well,
battery always.
Yeah. I would say it's usually the battery. And actually, it's one of the other kind of key points that I wanted to kind of talk about was the fact that a lot of people may be running too much kV, and that there's two reasonable ways of determining that. Firstly is if you're a freestyle pilot who's concerned most about punch outs from a hover or from very low speed, you can look at a static thrust table and go, well, can my battery actually provide 35 amps times 4? Can it actually provide 140 amps? If you've got your ESC set up with a current meter, so you can see in your goggles like what the current is, and you've calibrated it with a clamp meter or whatever, and you're not getting up there, you're not getting to 140 amps, then perhaps you might be running more kV than you need. And the other thing is, if you're a racing pilot who cares much more about straight line speed, the other test to do is to punch out full throttle in a straight line and see what you peak at on your amps, and then add a bit more kV. If go up a bit in kV and check to see that you're getting more current drawn, good amount more current. If you're not getting a good amount more current drawn, again, the extra kV is actually wasted for you. You're not using it. Right. Much better, actually, maybe to consider maybe a lower kV. I'd love to get Bob, get your opinion on that.
Yeah, Bob, you look like you got something to say.
It's too much kV is absolutely a thing. It works, but definitely you want to have the right kV for it. The whole motor has to be balanced. Like, you got to have the right stator to generate the right field torque for the right magnets, and have everything be optimized for each other. And that's where you get really the benefits of the motor. Like, there are other types of motors that we can use. We just don't, because they're too expensive to manufacture or design and make, and some of them just don't even make any sense. But like, we're stuck with this one subset of motor, and in order to maximize the motor and get the maximum performance that we want, or the style of performance that we want, it's all about just optimizing all the components. And to do that takes a lot of time and effort. And you can calculate up to some point, but after that, you have to actually look and see, like, is it overheating? Are my windings actually good? Did the binning of the magnets in this bell not work out? Like, what's actually going on? So it's management more than anything else.
Sorry, Joshua.
Chris, go ahead. Then I was
just going to say, just really quickly, something that I really want to work with Bob on is, I would love to try and codify his experience when he's trying things out, and work out what physical parameters are changing to give him that different feel, so that we can predict, if we change this thing, oh, well, that's going to affect flux density, or that's going to affect moment of inertia. And when we did that before, we had this effect. So now we can take this motor and make it more X.
About that, like I said, we're talking about a very small subset of motors. As you go down, everything is different. Everything is different. For some reason, as you go up, again, everything changes, from the props to the way the stator heats up and all the things in between. And also the quality of the components that you can actually get from manufacturers is also different from small to big. It actually costs the same amount to make a small motor, but nobody is gonna pay the same amount for a small motor. So they have to use crappier parts to make that small motor. So everything, that's a tiny thing. The physics also changes across everything.
I agree.
Also,
the physics doesn't change.
Yeah, well, that's what I was going to say.
No.
The physics stays the same, but everything else changes.
But everything changes around it. But the other thing is that these, like, people test 2306 versus 2207, and they can't tell a difference. Those two particular motors are very close in everything. So it's understandable that you're not going to feel a significant difference across the same manufactured motor. But in the real world, when you test like a 0.1 millimeter thicker magnet, you can absolutely very clearly tell a difference when you fly it. Just the other day, I was at the flying field, Apollo, and there were some like new pilots that I gave like my new prop to. And the first 5 seconds, these guys had no offense to them, but they were not highly skilled. And they could obviously tell a very clear difference between whatever they were running and this adjustment. And even the previous version prop that I had to the next version, which was a 0.03 millimeter change in length. 0.03 millimeters, a novice pilot was clearly able to tell a difference. So it's like, if you test it in the real world, you can absolutely tell. It's not like we're talking about things that are just so minuscule that it doesn't matter. It's very easily testable. You just have to do the testing, which is the pain in the ass part.
It is, yeah. Especially blind testing is ridiculously time consuming. I want to. We're about a half hour left in the conversation, and I want to shift it a little bit to try to help people. We're going to get right back into the weeds, I know it, but to try to help people pick the right motor for their application. So we've talked about all this theory, and it's been wonderfully wonky. But if somebody is choosing a motor for a given application, how should they start thinking about that? And Chris, I know you touched on this in your video. So since you're the one who sort of sparked this conversation, why don't you go first?
Well, I would say if you're looking for 5-inch freestyle motor, then 2306 or 2207 size, very, very good size. Even 2208, if it's as long as it's not going to get too hot. If you're going to be sitting high in the throttle all the time because that's how you like to fly, then maybe go a bit wider. But yeah, 2306, 2207 for a 5-inch.
Because the wider motor will have better cooling.
Yeah, that's right.
Okay.
So if your motor is getting really hot and you are confident that it's because of the way you're flying, as in you're high in the throttle a lot of the time, then go wider.
Good advice. Good tip. Solid tip.
If you're running a Cinewhoop or you're running other types of quads, again where you're high in the throttle, you're working the motor really hard. Yep, stay nice and wide. I would say be careful with ultralights. In general, you will always have more problems if you make the motor too small. A big motor is going to be fine. It's got loads of torque reserve. It's never going to have a problem. If you're looking to you're trying to do a 5-inch or something, and you're going down to like 1806, 2004. Yeah, as you start to reduce the size of the motor, it has less torque, and suddenly you start getting close to the point where you're going to get problems with flight characteristics. So if you're just a new pilot and you just want something that's going to work, err on the side of bigger.
So maybe we could start with the principle that your motor must be big enough in volume to have enough torque reserve to drive your prop.
To control the prop, yeah.
And then think about the shape of the motor as regards the cooling, whether the motor should be around a 3-to-1 or maybe a 4 or a 5-to-1 in terms of where you're going to be running it in the throttle curve and how much cooling it's going to need. And then people are going to ask, well, how do you know how big of a motor you need? You just need to look at what other people are using. Experienced pilots is the best way to do it. Who is going to jump in there?
I was going to say, I would add a couple of things, especially when regards to ultralights. You can get into trouble with ultralights, not because of the motors and props, but because of the frames if you run too heavy a motor, because the heavy motors have more torque, they have more moment of inertia, they cause a lot more flex in lightweight frames. So you kind of have to balance that. And also you have to remember that torque is proportional to current. So if you're going for a long range quad, the smaller, lower torque motors are generally going to be a little bit more efficient overall than the bigger, heavier torqued motors. So some of that depends on where in the loading point the prop sits and your thing sits. But as a general rule of thumb, a smaller motor that's running a little bit higher in throttle is going to sit in a more efficient range in terms of electrical efficiency than a bigger motor that's sitting lower in the throttle range at your cruising speed. So like all of that has to be taken into account, especially on these ultralight builds. The efficiency. Yeah. And
I'm gonna at the risk of shilling my own content. In the motor video, I have a little graph, a little chart, which helps you see roughly what sort of state of volume is appropriate for what diameter of prop. And there's a little bit of a description around that. So that's one thing that might help people. And the next video I'm doing is going to be on how to pick the right prop diameter for the weight of quad that you want to build. That probably will also be a little bit controversial. So
I think one thing that we're coming back to, and Bob, I want to get your input on this too, is that the entire motor selection is driven in large part by the prop selection. You're going to pick your prop based on the size of quad you want to build, and then you're going to pick your motor based on the prop that you've selected. Bob, you also have a spreadsheet that sort of looks at motor size versus prop. Bob, how do you size a motor based on the prop that you've selected?
So what I'd recommend to people is look at the prototype size of motor for the given prop. So like 2207 is like the prototype size for a 5-inch prop. If your quad is going to be drastically heavier, well, you just need more power, period. So you want a bigger motor. But if you want more efficiency, you want a smaller motor, which you're going to sacrifice control and performance, but you're going to get more efficiency. So like these long range 4-inch things that are running like 1304 motors on a 4-inch prop, which is ridiculous in my opinion. Yeah, they're going to give you great flight time, but you're going to have very, very weird control issues with them. And that's the limitations. And as I've learned firsthand, having a big motor on a skinny little frame is quite the challenge. It's quite a challenging thing to do. And so the motor that I'm redesigning the 2303 and 2203 and 2204 to actually try and reduce their weight and increase their performance with this newfound information from the issues that I've had with the 2506, to try and get something that's going to further optimize all of it together. But yeah, that's my graph also looks at the stator volume versus the surface area, which is very similar to Chris's. I mean, it's essentially the same graph. You're just multiplying it by different numbers. And so that is the graph that I use, not necessarily to choose a motor, but more to just look at the sizes that I've tried and understand my experiences across all the sizes. So that's really what I look at to figure out what I want. And there's a theme in the chart as well. There is like a golden proportions to prop size and motor size as you go down in prop size. And there's also like lines that I've drawn in there that tell me that, okay, so these are the motors that I've liked. So this trajectory should be similar, at least within the prop size. And also motors that I can clearly see that have overheated in flight. I know that this line, I can't go under it, because then I know that I'm going to have a motor that's going to run too hot, even me as a human to be able to tell. So I want to stay well above this line to achieve that. But then also you throw the KV in there, which isn't even on the graph, and it mixes everything up further. So unfortunately, it's just experience has a lot to do with it, and we don't have like a good quantifiable way to look for specific sizes for specific prop. And the prop changes drastically. Like everything changes about the prop from one prop to another.
Bob,
I think it's important to note, though, and we've mentioned this a couple of times in this chat, that most modern motors are going to give you a result that's completely manageable.
Yeah.
Like,
right.
Well, as long as you're in the ballpark. Like I talked to a guy this week. He said, I have a 3-inch quad, and I had some 2004 motors. They're 2004 2750 kV or something. And he was like, they're super hot, and I can't get it into the air except at 60% throttle. And I was like, you've just picked the completely wrong motors. Those are too big. They're too heavy. They have excess weight. They have more torque than they need, and they don't have enough RPM to spin the prop. I mean, Ryan, you got to be in the ballpark.
Yeah,
and I
right. I mean, even that, he could probably fly it if you put a higher voltage battery on there. But
maybe.
But yeah, I mean, yeah, you got to be in the ballpark. But if you look at what other pilots have had success with, if you look at examples of other people's builds, like on rotor builds or whatever, and pick something close in the same KV range and then in the same size range, you're gonna get a decently flying quad. I mean, like the differences that we're talking about, I think it's really important to note that the differences that we're all talking about here, like when we're talking about optimizing these designs and stuff, these are differences in a fraction of a percent of performance. I mean, it's feelable, it's noticeable if you're an experienced pilot. Could you necessarily tell a difference in a video if you flew two back to back and the pilot was just adjusting to the differences on the fly? Probably not.
Yeah.
You know, the pilot could feel the difference, but would someone else be able to tell the difference? Probably not. I mean, we're talking about really, really tiny differences in performance here.
People can definitely tell.
Bob, I want to ask.
Pilots can tell.
Chris, you've posted your spreadsheet that you talked about. It's in your video, showing the size of motor you would recommend for a certain prop. And Bob, I've seen your spreadsheet, but I don't think you've published it anywhere. Bob, is that true, Bob?
I have a link on one of my videos. I also sent you the PDF. You can post it. I mean, if it's
all right,
helpful
I'll put a link to that it's not there right now, but I'll add that to the description of this video, because it does encapsulate a lot of your experience flying a lot of different motors. And like Ryan is saying, if you get in the ballpark with a motor, you'll be doing okay. And I think that's going to get them in the ballpark.
And then as you get experience, I mean, that's where it comes down, right? So your first build, you shouldn't be obsessing over these kind of details, right? Like your first build, you can do something that'll get you in the ballpark, get you out there, get you flying, and start getting stick time. You know, as you get better, as you progress, then you're going to start looking for things that accomplish specific needs for your specific approach. So that's where you're going to start to fine tune some of these details and figure out, oh yeah, this is a lot better. Now, to be fair, a good flying quad is going to make it easier for you to progress than a bad flying quad. So, like, but again, it depends on how far off of the mean you are. And in general, I think a lot of new pilots aren't struggling because of small differences in hardware. They're struggling because a build is just bad to begin with. Like,
Right.
Their tune is completely off, or, there's bad hardware that they damaged during assembly, or, there's all kinds of other reasons that make your quad fly worse other than small variations in motor size.
Okay. Let's see. Where do we go from here? We got about 20 minutes left. We talked about choose a prop and choose a motor that fits that prop. We talked about the weight of the motor mattering at the end of the arm. You don't want the motor to be too heavy, but if it's too small, it'll get overheated. How about KV? How does KV come into play when someone's trying to, like, they got 1800, 1900, 2100 KV motor, and they're running 6S. How are they going to pick the right KV for their application? Chris?
Well, so the first thing I would say is to think about how you want to use it, how you want to fly. And my flying style, I don't really spend a lot of time at 100% throttle. I don't really care about whether my quad has a 10-to-1 or a 10.5-to-1 thrust to weight ratio. And so I tend to pick the lowest KV that's offered for the size of motor, So I run 1700 KV on all my 6S rigs for 5-inch, and I love it. It's the nice thing about that is it's kind to batteries. My batteries cope fine with it, and when they get a bit old, it's still okay. Nothing sags out horribly. So I think I play it fairly safe on KV. But if you want to go higher because you want that extra performance and that real, instant acceleration and huge top end that you get with the higher KV stuff, just make sure that you're not. Just make sure that your battery is keeping up.
Right.
So if you're running a 2100 kV motor on 6S and you're buying, like, I don't know, what's a cheap battery make? I don't want to like slag him.
Well, let's just say you bought a 70C battery by accident.
Yeah.
From anybody.
Then you bought a low C battery, or you've got batteries that are old, a bit tired, they're struggling. Like, it's not helping. You're not doing yourself a favor. So if you're going to go high KV, make sure that you're really buying like 120 C rated batteries from your battery testing, Joshua, is fantastic for that. Pick the battery with the highest current ability to supply current, so that you can feed those motors. Because if you want the torque they can give you, you need to be able to give them the current. And if you can't give them the current, then you might as well not bother.
What about the weight of the quad, Bob? How does the weight of the quad come into play?
Massive.
Especially as you talk about micro quads, even a few grams of weight makes a difference. How does that relate to the motor selection and the KV selection?
So you have two different things here. You actually have the overall weight of the quad with respect to the power performance, and then you have the overall weight of the quad with respect to the control performance. The two are very different. If you think about a plane, the control surfaces are the flaps. Larger surfaces give you a lot more control. So for any given weight, having a larger prop, which is your control surface, is going to give you more control. And it's also going to change the control quality a little bit. A quad that weighs less for a given prop size will be overall less skittish. It won't slide around easily, and you'll feel like you have more of a grip on the quad because it's not going to skate across the sky randomly at like 2-degree tilt. I actually just finished developing a 5.21 inch prop for these GoPro 8, 9 carrying things, just because the damn thing is so heavy now. It's up at 750 grams that it's just too much weight for a little 5-inch prop. Once you get higher in the weights for a given 5-inch quad, past about 650 grams, all the props start feeling very similar because they're all struggling to just produce thrust. Like, you just can't do anything with it. So once you get too high, it's just everything goes down, like all the performance drops. So obviously lighter is always better. And that's the main struggle that we have on anything that flies. Lower weight is always going to perform better with the same parts. I'm not saying sacrifice battery or motor or frame or anything just because you want to drop weight, but you have to have a balance there. So when you go down in size, and particularly down in power, a long time ago, when Chad Nowak was still around, he actually did a bunch of testing and came up with some numbers for the smaller quads. And he said that a 3-inch prop should never really hold more than 90 grams is the max weight of a quad with a 3-inch prop. And that's so interesting because now that we have that, I'm running my little 1S things. And once you get past around 90 grams with a lithium ion battery or whatnot, the performance just drops off a cliff. Like, it's terrible. So for any given prop diameter on a quad, not like an octo or anything weird, there is a certain point where the performance for that prop size starts to taper down real fast. But up until that point, it's not really going to change that much. So like for a 3-inch, if you go below about 72 grams, you're not really going to get much benefit other than flight time and maybe some speed. If you go past about 83 grams, that's when it starts dropping off a cliff. That's when it starts getting really bad. Regardless of the amount of power that the quad has, sure, you can go faster with a bigger motor and a bigger battery and whatnot.
There's a relationship there, which is that, so as weight goes up, you have to make more thrust to fly the quad. You can do that by spinning the prop faster. In other words, by increasing the kV of the motor. You'll, of course, draw more current and hit the battery harder, but we could set that aside. But as you spin a prop faster, what happens to your efficiency, Chris or Ryan, whichever one of you wants to take this? Because I think your efficiency is worse, isn't it?
So actually, this is I'm now going to spoil my next video, but that's okay.
Aha! That's the reward for watching all the way to the end of the live stream.
Yeah, that's it. So I'm, based on the analysis that I've been doing and the research that I've been doing, I believe that, I think based on what I've looked at, that a tip speed of about 450 miles an hour at wide open throttle is about where we should be aiming at. And what's really interesting is that tip speed, 450 miles an hour, is the same for full-size helicopters, the same for turboprop planes, and the same for 5-inch mini quads.
That's fascinating.
Very interesting.
And I believe that the fundamental reason for that is, so it's because they're all in air. The air is the gas. So compressibility effects occur above a Mach number of about 0.6, and compressibility effects hurt subsonic aerofoil performance. And a 0.6 Mach is just about 460 miles an hour in air. So I believe that when we're scaling our quads, and this is what the video is going to be about, whatever size quad we're making, I think that we should be targeting a tip speed of about 450 miles an hour at wide open throttle.
Interesting. Siati wants to know in the YouTube chat whether that number is affected by the pitch of the prop.
So the pitch of the prop has lots of effects. It changes the angle of attack, and I did a video looking at the factors that affect props, and talked a lot about inflow velocity and pitch and relative angle of attack and all of that. But the short answer is I don't believe that the pitch of the prop changes that optimum tip speed, because a turboprop plane has a variable pitch prop, so it changes its angle of attack in flight, but the RPM of that prop is held constant at cruise to maintain a approximately 450 mile an hour tip speed.
And what that would mean then is that for each size of prop, there would be a motor KV that would produce that there would be sort of an optimal motor KV. And I guess people are going to have to watch your video to hear. I don't want to completely spoil your video.
I think that's important to note, that's where the pitch of the prop is actually going to impact this, because the amount of RPMs that a prop can hit at a given KV is going to be hugely impacted by the pitch of the prop. So a heavier pitch prop may need a little bit more KV to get to that tip speed.
Yeah.
But
Right.
then you also run into that issue of that's going to change depending on the inflow velocity of the air. So, you really have to think about these relationships. And there's a really important point in this all. When people are doing these calculations, a lot of times I see people making the mistake of taking the kV of the motor, multiplying it by their voltage, and then multiplying it by the diameter of the prop to get the tip speed. And it's that is not accurate, because the loaded RPMs of the motor are completely different from the unloaded RPMs, and they vary dramatically depending on the torque load that's being applied to the motor.
And thank goodness we have bidirectional D-shot now, which lets us look in our black box log to see the actual RPM in flight. But it does. I can see that. Again, going back to the Cinewhoop versus freestyle quad, if you're going to be tuning a Cinewhoop where you're going to be at constant RPM versus hitting max RPM and so forth, you're going to be tuning that differently.
So regarding tip speed, 450 miles an hour is about the optimum based on my research for getting performance. For getting efficiency. So for getting good balance of performance and efficiency, you can go faster, but once you get up to about 0.8 Mach, you start going into a transonic regime where you'll see a lot of vibration and losses and stuff. So you want to be careful. I mean, I don't think that many mini quads will be able to get up there, to be honest. We just don't have the torque. But
Chris, I'm not doing the math here on stream. Obviously, you can see that. But Mr. Huggy in the chat says something doesn't add up here, because if the optimum tip speed is 450 miles an hour, that would mean a 6-inch quad running on 6S would need a 3,500 kV motor, and we know that if you did that, you would just destroy your battery. That's way too high a kV for 6-inch.
So 6-inch.
I don't think
for a tip speed of.
Is he messed up his math?
I'm just checking. I've got a prop tip speed calculator here. So we're looking for a 6-inch at about 25,000 RPM.
Right.
Which is I don't know what that works out to as sort of a. Ryan's going to do it. Thanks, Ryan.
So what are we assuming? 6S voltage?
6S. He said 6-inch quad, 6S.
25. That would be. Hang on. What was it? What did you say it was? It said 25,000 RPMs, right?
He said. Oh yeah. Okay.
Yeah, that's 1,200 kV.
Oh, so he's just done the math wrong.
I mean, and that's 1,200. That's 1,200 kV at under load, right? So if we multiply that by, you can generally get away with about. It's usually between 70 and 80% reduction under load. So if you divide that by 70%, you're looking at probably close to maybe
like 1,700 kV.
Yeah, 1,700 kV or so would be.
Which is pretty reasonable,
right.
actually, for a 6-inch on 6S.
Yeah. That's maybe with that 70%. That feels a smidge high, but with that 70%, that's probably right about on. Mr. Huggy, we'll take a look at your Google Doc. I think maybe I'll forward that to Chris and he can weigh in. But I think here in the last 8 minutes of the stream, I think we're not going to dive into that spreadsheet.
Yeah, someone just posted their 6-inch quad on 4S at 1,900 kV is hitting about 2,200 RPMs.
Okay, cool. Well, that's getting up there.
Yeah,
that's getting up there.
That's close.
There's a question from Crash Day in the Discord saying, how do you compensate for more weight? With the let's say you've got your motors and your battery, you're all locked in, but your quad, let's say you put the GoPro on and now your quad is 150 grams heavier or something. Well, how can you compensate for that with changes to your props?
So
bigger.
Bob, you want to weigh in here?
Bigger.
Go ahead.
Bigger.
I love it.
I mean, but if you're locked into the frame, right, and you can't go bigger,
right?
Going more.
Well,
let's
say you've got a little wiggle in your frame. Would you go to higher pitch or higher diameter first?
Higher diameter.
Higher diameter.
Yeah.
Diameter. Yeah.
And I consider more blades as well, like Ryan says.
Going from 2 to 3 or 3 to 4.
Here's something really interesting. So I've been playing with the diameter quite a bit, and for 5 inches, just special diameter. Once you go past a certain point, it just starts to feel bad. The pitches of the props that many of these manufacturers make are not in their name. So a prop might say a 5.1 4.33, but it's not a 4.3 pitch. That prop is actually a 2.5 pitch.
That's just a marketing number, isn't
Well, and
it?
the truth is,
It's
like,
just a marketing number.
the Proch is
So here's the crazy thing.
That's so frustrating.
So here's the crazy thing. If you go to my new prop is a 2.6 pitch, and it's 5.21 inches, not 5.1. So that prop is faster than the 5.1466, which is actually like a 3 pitch, but it's only got a wider diameter.
well, and the pitch also is not consistent, right? So like,
Right? Yeah, it's not
the way
really
the
a pitch to bat.
changes over the prop actually has a huge impact on its performance.
Right.
So where in the position away from the hub the steepest pitch part of the prop has a huge impact on speed.
But you kind of hope that they would try and adjust the pitch because of the the tangential velocities at the point of cruise.
It is.
Right?
It's and they're doing a pretty good job of that in terms of the airfoil design and everything. But like translating that into a specific pitch that they can slap on a label is complicated.
Yeah.
All right. But in general, and Chris, you've got a video about props that people can watch, but in general, a larger, longer diameter prop is going to be more efficient than a smaller prop of higher pitch that makes the same thrust. So if you have the option to go to a larger...
It's not just efficiency. I focus more on control. The issue is the disc loading. When your disc loading is just too high, it just sucks. It just feels like crap.
Yeah, well, you need bigger changes in thrust, bigger changes in RPM to achieve the thrust that you need to control the craft, right? And so the whole system then is going to struggle more. Both the prop, the motor, ESC, everything is going to be struggling a bit more.
All right. Let me get a couple more super chats out of the way in the last few minutes of the stream. Mechanikern, thank you for 50 Norwegian kroner. You might not feel the difference in torque, but the time the torque is needed, so a more powerful motor changes the timing in flight. I feel like that made more sense in context at the time it was sent. Sorry for leaving it to wait.
It speaks to responsiveness, no, right? A bigger, more torquey motor responds more quickly. Therefore, everything happens sooner, which is good for us.
Yeah, definitely. Schlopnat, thank you for 20 euros. Thanks for your help with my recent receiver problems. I switched to Tracer and I could not be happier. Yeah, how to fix the problems with your receivers? Just buy a different receiver. Definitely. Yeah. Peter Pan, thanks for $5. One of your best streams. I'll all credit to these incredibly knowledgeable people. Thank you so much, you guys, for spending 2 hours of your Sunday afternoon talking to me and talking to these folks. And I think we're caught up. Yes, we're caught up on super chats. Guys, in the last 4 or 5 minutes of the stream, anything that you'd like to add or mention or plug? I've got links to all of your websites and YouTube channels down in the video description so people can check those out. Chris, any last words for us?
I don't think I have much to say other than it's been really, really nice to have this conversation. I'm really glad that people are feeling like what I'm doing is valuable, and that it's contributing in a positive way to the knowledge that's in the community. I'm thrilled to be able to work with guys like yourself, Joshua, Ryan, and Bob, to help you guys in what you're doing, and I hope I'm going to be able to continue doing it for a little bit longer here.
Yeah, awesome. Thank you, Chris. Ryan, any last words for us?
Oh, it's been a good discussion. I think that this is something we could continue to discuss for a very long time, and still, and I think there's a lot of room for us still to make progress. So it's been fun.
Yeah, Bob.
I'm just thrilled to be mixed in with these guys.
Yeah.
If anything, it's a lot harder to get things made and done than anything else. It's really hard to get things made, and I would recommend everybody buy everything they can find right now, because everything's going up in price 30% minimum over the next couple months.
You're not kidding. Emacs recently released a new price sheet. One of their retailers forwarded it to me, and everything, including motors, like Y Motors, everything was 20 to 30% more expensive. You're not kidding.
That's just the start. That's the start. It's going to go more.
Yikes.
It must be
I don't wanna hear
because
that.
companies are trying to spread out the cost increases on certain things, right? They don't want to hike the cost of a flight controller by 100%, so they lift everything, right?
Maybe so.
Right.
I want to thank all of you guys, of course, for coming. By the way, somebody wanted to see my shirt, FPV Flight Club. Unfortunately, out of business, but you may still be able to order this shirt. There you go. I want to thank you guys, of course. Thank you guys in the chat and in the Discord for coming out. I'm super excited, Chris, to see that all of the work you're doing is being paid attention to by folks like Ryan. It would be very easy for a frame manufacturer, not going to name any names, to take your criticism and say, you know, screw you, how dare you, my frames are amazing. But there's no doubt that the work you're doing has value. It's amazing that you're providing it for free, because you certainly could be charging for it. And I'm really excited.
No one has done that, by the way. No frame manufacturer that of whom I've done a video of has been anything other than quite receptive to working together.
Fair enough.
Across the board. So, in my opinion, you know, a lot of people out there are taking this seriously and wanting to make better frames for people. So no one's sticking their head in the sand on this one.
And I'm very excited also to see you in the same room with Bob. I feel like, as I said at the beginning, Bob got a little heat from your comment section, and it's very nice to see Bob's experience being taken seriously, because I think it deserves it, and to find a way to codify the great resource that he is. So we are going to wrap up. That's going to be the end of the stream. If you missed any part of the stream, the replay is on my channel. But we're going to get out of here. And if you are on my Discord, I'll be there in about 10 or 15 minutes after a bathroom break to play Among Us. So that's going to do it, though. Happy flying, everybody. We're out of here. Yeah.